And this is what Bohr tells us, right? That's a very fundamental thing, this quantization and energy level. And so you have these absorption, and you see one peak. Okay, so that's typically what you see in spectroscopy. Now you look at a solid, right? Look at a solid. You can excite these things from field state to energy state. And what do you see? You see what you see is that you see a rise, right? So once you have enough energy to make this crossing, you have this rise on here. I'm not drawing very well here. So you have this rise, so it's the onset of the absorption. So this is the band that you see. So you see an absorption band on this. Now, I also try to draw some of this little vertical line. And what are these little vertical lines? That's an interesting phenomenon because the vertical line corresponds to some so-called exciton energy. Okay, so exciton energy, let me just jump a little bit ahead here. So here we have an exciton is an excited state of the solid where the electron doesn't quite make it to the conduction band. So imagine that the photon comes in, ejected this electron from the atom in your lattice, right? And the electron is traveling outside your lattice, starting moving away from the lattice. But as you go out, it created a positive charge, right, in your atom inside. And this positive charge exert a force on this electron, and essentially trap the electron in some temporary state. And so the electron starts coming out. The positive charge in here starting to attract this thing, right? So exciton is really correspond to an electron hole pair. In fact, it's an electron hole pair. This electron is somehow, it doesn't quite make it to the conduction band. It's somewhere in the middle, inside the band gap. Okay, so when you see discrete energy, this corresponds to exciton energy because that's a virtual, so-called virtual state. Is a weird phenomenon because you would have thought that, well, in the band gap there's an empty state. How could you see this? And that is due to a physical electrostatic phenomenon that as the electron go out, the core hole left behind starting to attract this electron and trap the electron in some temporary state, and this is the so-called virtual state, and this corresponds to the exciton energy. So sometimes when you read, for example, literature, and you read zinc oxide, and it has a 3.4 eV band gap, right? And this corresponds to 3.4 eV here, right? And then it tells you it has a 65 millivolt exciton energy. What does that mean? Well, it means that up here, just slightly above 65 millielectron volt above, there's an energy level that you can actually put electron in that exciton energy level. Okay, so that's a very interesting phenomenon because that leads to consequences in electronics in many ways. Okay, so you have exciton energy is in between this, inside the band gap, right? Is where you should not expect to see electron, but then due to the trapping of the core hole, it's the force of the core hole, you have this exciton, and the exciton exists inside the band gap. Okay, so that's a nice, interesting phenomenon, and you see this when you read literature. You see it from time to time when people talk about exciton energy. Okay, so measuring the threshold of the alkaline is a simple way, right? So we just look at the onset of this band. For finding out the band gap, so you just check, if you can run your UV spectrometer, right, just like in liquid, in transmission mode, you can see when the onset, you scan the wavelength, you find out when the onset is, and you will see, you can then deduce that this is the band gap that you have. You are making a semiconductor or insulator for that matters. So in the case of, there's additional peak. I say that in the case of this thing, there's additional peak, and that is due to the absorption caused by exciton. So the little two peak that I see here, I try to draw there are exciton energy corresponding to exciton energy. You see a little sharp peak. You gotta have enough instrument power to do this because they are hard to find. You have to have enough resolution to detect this exciton energy, and they are usually very low energy, right? Mini-electron volt and so forth. Okay. The other thing that you can talk about these material as a consequent electronic structure is the thermal excitation of these, and these require a little bit. Try to jog your memory in thermal physics or statistical mechanics. Some of you may see, may or may not see. So I'm going to just give you a very quick introduction to this, some mention of this, just to identify what is these thermal excitation reactions. So we have optical excitation, and then we have thermal excitation. Of course, the word thermal implies we are playing with temperature, right? We are working with temperature on this. So it is in effect is the temperature dependent of your electron excitation, right? So here we have from the ground state, if you excite thermally by putting it here on the ground state, what happened is that the number of density of the electrons depends on the temperature. Okay, so the number, so-called, so the number of atoms, actually the number of atoms or molecule in the excited state, right, in the excited state at a particular temperature is given by the Boltzmann distribution. So here you have n's of I here, so think of it as the number density of the atom that you can feel. And of course, this corresponds to the electron as well that you have. Right? So the Boltzmann distribution simply said the number is inversely proportional to e to the, so it's proportional to e to the minus ei divided by kT. This kind of expression occurs in chemistry very often. This sort of the inverse exponential decay type phenomena occur quite often. Arrhenius-like dependency, right? So and this energy E of I here correspond to the energy of the state that you're talking about, and K of course is the Boltzmann constant that you have. So basically, what is it telling us? It's telling us that the number density depends on the higher the energy, the less likelihood you see population there, right? Because it's a exponential dependence on this energy that you have right here. So what you got then is that for electron, we must take into account. So for number of molecule, you don't need to worry so much. For electron, we have to take into account Pauli exclusion principle because you cannot fill. So when you are populating the state, right? So you're filling boson and fermion are different. So they have different statistics. In physics, we talk about these with indigo spin or non-indigo spin, right? So electron is half spin 1/2, and is controlled by this Pauli exclusion principle. Is fermions, right? And all fermions must not have the same spin orbital. Spin orbital are orbital with the addition of the spin. Okay, so because you in the case of electron, you have spin 1/2 or spin minus 1/2, right? So there's two possible spin state. At the most, you can put one electron with two electrons with opposite spin. Okay, so in one orbital, in one space orbital. Okay, so you have to sort of count it in a certain way, given the Pauli exclusion principle, and also the electron you cannot distinguish electron in atom B from atom A, for example. If you exchange the electron, all of the electron in atom A, and then put in NMP, you will not know the difference, right? So you have to also account into this idea in this the idea of exchange equivalency, that when you exchange the electron, you cannot identify or distinguish them in this. Okay, so if you take into these two principles, what you got is that you lead to so-called Fermi-Dirac